Hi, we are Team 9. I am Deanna Garcia, and today we'll be discussing the dynamic characteristics of a 2006 Saturn Vue SUV. Our objective is to determine and measure the vehicle's turning circle, steering ratio, CG location and height, weight on each wheel, analysis of load transfer during acceleration and braking, analysis of load transfer, in addition to determine the vehicle's braking, forward, and lateral acceleration utilizing the VC3000. Here are some pictures of our vehicle, our clock slides. And just to review some specs of our vehicle, our Saturn has a 2.2-liter gas inline 4-cylinder engine, a 4-speed automatic transmission with overdrive, a front-wheel drivetrain. Suspension consists of independent front and rear suspension with anti-roll bar and rear and front coil springs, a power-assisted rack and pinion steering system, and power front disc and rear drum brakes. Now, the first thing we want to determine about the vehicle is its turning circle, also known as its turning diameter, which is the smallest circle in which the vehicle can make while turning. We're going to measure the distance between this center to the location that the tires come in contact with the road. We're going to compare this to the curb-to-curb turning diameter, which is specifically the diameter of the smallest circle within the vehicle can clear a curb of 150 millimeter height while still executing its sharpest turn. We look at the geometry of a turning vehicle as seen in the figure. We're going to assume low speed and level ground, which results in no slip on the rear wheels. Because of this, the center of the turn must lie on the projection of the rear axle. Consequently, the perpendicular from each front wheel should pass through the same point, which is the center of the turn. So we took this knowledge into the field, and we took our vehicle and made it perpendicular to a straight line and fully turned the wheel to the left. We then pursued at low speeds, keeping the wheel fully turned, and made a circle. We stopped every few feet to mark the orientation of the front tire, and then returned it to its initial starting point. We then measured and connected these circles to enclose the turning circle and measured its circumference and diameter. We found our results to be 20.6 feet, which is a difference of only 0.9 feet from the manufacturer's value of 19.7 feet. Discrepancies could be due to the fact that we measured from the inside tire rather than the outside tire and then added the track value for this finding.
My name is Allison Embry, and I will be discussing the steering ratio. The steering ratio is defined as the angle of the wheel to the angle of the tire. The hardest thing to really find about this is the angle of the tire. One of the ways we did this was to first crank the wheel to 90 degrees, then draw a line with chalk parallel to the tire, crank it another 90 degrees up to 180, draw another chalk line parallel with the tire, and thereon from 270 to 360 degrees. And we also drew one from 0 degrees. From there, you can find the angle a number of ways. We decided to go with 3 ways. The first way was to just take a protractor and set it on there and just see if we could figure out the angles. There are some discrepancies about this. The chalk lines are really thick, so it's kind of hard to see exactly where it is on the angles that you can do. The other 2 ways were through trigonometry and geometry. We measured all the lengths of the various triangles and went from there. This table displays all of the angles we got and their corresponding steering ratios. So up here in the very first tire angle table under protractor angles shows you the angles that we were able to get from the protractor, and from there in angles from cosine and in angles from sine we calculated those angles. As you can see, they are very different from one another, which should not be the case. They should be the same. Some reasons for this are we didn't use a ruler to draw our lines, so they looked straight to us, but they may not have been straight enough. From there, we calculated the corresponding steering ratios to all of these and took the average of each of them. So from here, these are the average of the 3, and then the average of those 3 is 26.27. So we've taken our steering ratio to be 26 to 1. So with a steering ratio of 26 to 1, literature reports 17.8 to 1. So we're 37% off. A big reason for this may be because my car the View was in an accident, and this may have knocked off the steering ratio. Also, the lines were not drawn straight.
I'm Joshua Moran, and I was in charge of finding the CG location. We did that by getting the tire impressions onto papers, and you can see that here. We measured the area that these impressions made on these papers, and then we applied definition of the pressure, which is force over area, to them. Now the pressure that we got was, we actually took that from each tire. We took the PSI using a measurement tool, and then we rearranged the equation so we can figure out the force on each tire. The force on each tire here is shown in this table with a total weight of a vehicle in pound force of 4423, which is only a 10% difference, which is pretty good. Now this is a diagram of the free body diagram of the vehicle. The L stands for the wheelbase, C is for the distance from the rear axle to the center of gravity, and WF stands for the weight of the front axle. And so when you do some of the moments around A, you actually get that equation. But since we did this statically, meaning that there was no motion, and it actually was on a level ground, you actually get a simplified equation to WFS is equal to W times C over L, rearranging for C, once again, which is the distance between the rear axle and the center of gravity. And using the fact that the wheelbase is 8 feet 7 inches, we were able to figure out that the CG is actually located 4.69 feet from the rear wheel. We also did this calculation with the track width, and found that the CG is actually 2.7 feet away from the left wheels. This places the center of gravity near the right passenger seat on the left of that. And we estimated the height to be about 20 inches, 8 inches clearance from the ground to the bottom of the car, and another extra, a foot extra. For the next part, we're actually going to put the vehicle on unlevel ground and figure out the height of the CG that way using the moment equation that was shown earlier. A couple of discrepancies. Well, we did measure everything we had was measured. Nothing was completely 100% accurate, and that's where we think we got the 10% difference from.
Hello, my name is Steve Perez, and I'll be discussing how we did our VC3000 testing. We found an open lot 11 of the school. It was pretty level ground. It's over by the daycare. And what we did is we tested the braking, accelerating, and turning G-forces on the car, both in the X and the Y direction. So when you're accelerating in your car from 0 to 20, from 0 to any speed, you're going to feel a force of you kind of being thrown back into your seat. The same force is going to be felt by the tires. The rear tires will feel a greater force than the front tires during this acceleration. After steady state acceleration and you achieve a steady state velocity, you will not have this load transfer anymore. So during these seconds that we were accelerating, a G-force of 0.145 was found to be our average G-force accelerating from 0 to 20. That calculates a W sub R, or weight transferred to the rear axle, to be 2,131 pounds. From the static rear force is actually 128 pounds greater than what it was. And during our peak value was a 0.290 G force, which averaged out to be a 253 pound transfer to the rear axle. For braking, also if you're in a vehicle and you brake really hard, from any speed immediately to 0 in a couple seconds, you're going to feel a lurch forward. The car will feel that as well, meaning a load transfer will be transferred to the front axle. We calculated or measured a negative 0.545 g-force while braking, and a peak value of 0.682 g-force. From calculations, 2,873 pounds was found to be what the front axle was experiencing, or a transfer of 453 pounds to the front from static. And at our peak value, it was 570 pounds. Now for turning, if you make a sharp left turn, you'll be thrown in your vehicle to the right. Hopefully you're wearing a seatbelt at that time. So using these variables, all of these are known. At a g-force of 0.12, assume you're turning left. The right two tires will have transferred 174 pounds. And here is a quick little demonstration of how we actually did our braking test in lot 11. Yeah. Thank you.